So this screencast piggybacks off the last one. The last one delivered some content on how we find volumes of solids of revolution. And I wanted to write this in black. So we pick up with example 3. And in example 3, we have y equals radical x and y equals x. This is the region R between them. We're going to take that region and revolve it about the x-axis. When we revolve this region about the x-axis, it gives you a solid, right? But that solid has a hole in the middle, right? This is removed. And the solid that remains is just this part, right? So we're looking to find the volume of a solid with a hole in it. Well, what happens? You take your representative rectangle, you revolve that around the axis, and it creates a tuna can, right? It creates a tuna can with a tuna can size hole in it. So how does that work? Well, you find the volume caused by the big tuna can, right? Pi function squared dx. And you find how big the removed space is. Pi, integral of pi function squared dx. Both of those run from 0 to 1. 0 to 1. Pausing to make sure you know that. And then what do we do with those? We subtract those answers. The big blue tuna can comes from this. The little red tuna can comes from this. What we want is the area in between them. Now, we can make things easy on ourselves and make one bit. I should go purple. I should go purple. I think I tried. We can make one integral out of this from 0 to 1. There's a pi that can come out and cool on the windowsill. And then inside, you got square root of x squared minus x squared. We can do this as one integral. I'll leave it to you to figure out that this turns out to be pi over 6. Because I just want to demonstrate how this process works. I'm not as concerned with the Calc 1 stuff, although you're free to ask about that when we gather. Then things get a little bit more complicated if we do this. So here's y equals x, and here is y equals x squared. This is the space in between them. What I'd like to do is revolve about this line. Y equals -1. That's the axis of rotation. So again, you get a tuna can generated by the red function. And then you get a tuna can within that tuna can generated by the blue function. So you have a big radius generated by the red function and a little radius generated by the blue function. Now, in both cases, we're doing an integral from 0 to 1 of pi, which can come out and cool on the windowsill, times radius squared. right? Both of those are radius squared. And we're going to take the big radius squared minus the little radius squared. We can put our integrals together like that. So how big is the big radius? Well, the big radius goes from x down to -1. So it is x minus -1. The little radius goes from x squared down to -1. So that's x squared minus -1. And so this single integral, which is really the difference of two integrals, gives us the volume of the solid generated when region R is rotated about that line. Now, I'll leave it up to you to prove that that's 7 pi over 15, but it is 7 pi over 15. I'll go one more. So in this case, you have the function 2 minus cosine x and the function cosine x. This is the region between them. From 0 to, this had better be pi over 2, right? Because cosine x hits the axis at pi over 2. This is the region. Let's revolve that region about y equals 3. Let's make that the axis of rotation for this example. So again, you take something that's going to have a hole in it and you revolve that about y equals 3. So what is happening? Well, the red curve is generating the outside edge. It's further away from the axis of rotation. So the big radius is this one. And then there's a hole in the middle of your solid, and the hole in the middle of your solid is generated by this curve. It's closer to the axis of rotation. So because this curve is closer to the axis of rotation, it is generating the hole that gets removed. And in both cases, we've got an integral from 0 to pi over 2 of pi cooling on the windowsill times a function squared, a radius squared. It's pi r squared. And then we minus a pi r squared, and there's a height. So what's the big radius? Well, the big radius goes from 3 down to cosine x. 3 down to cosine x. The little radius goes from 3 down to 2 minus cosine x. From 3 down to 2 minus cosine x. And then, because we haven't talked about how to solve integrals of this type, we ask our calculator what that is, and our calculator gives us a decimal approximation. So what's the key every time? We take a representative rectangle, we revolve it about an axis. You'll notice that this rectangle is cut perpendicular to the axis of rotation. That's true in all of ours. The rectangle is perpendicular to the axis of rotation. The rectangle is perpendicular to the axis of rotation. So we take that representative rectangle, we turn it into a tuna can, and we measure a radius carefully. Then sometimes we're able to do the work, and sometimes we're not able to do the work, and that's fine. Hopefully these examples are illustrative, and there will be more when we gather.